Hello, can you hear me okay?
Yes, yes.
Perfect.
Yes, yes.
Hi.
Okay, fantastic. Okay, so as you can probably see from my surroundings, I'm actually in the Atlas Cavern at the moment, just about 100 meters underground. And so what we'll do is, what the kind of format for this virtual visit is gonna be is that I'll give you a sort of a brief overview of this endeavor that we call particle physics, and then our organization that we sort of work at, CERN, and the facilities that we make use of in the Large Hadron Collider, and then we're going to focus down onto the specific experiment that I'm a part of, and that is just over to my left, and I'll kind of give you a look at that shortly. So I'm just going to, okay. If I could just have permissions to share the slides, and then I'll do a little talk.
Adam, yes, sure. Working on it. Can you share it?
Not yet, no.
Now you should, yeah.
Okay. So here we go.
Okay.
Okay. So hopefully you can all see this now.
Yes, we can.
Okay, great. Okay, so first of all, I suppose I should say thank you to everyone for coming to visit us down in the cavern virtually. So like I said, so just have a quick look at our kind of tour itinerary. So I'm going to start just by explaining a little bit about what the physics that we're actually interested here is and what it's all about. Then we're going to look at CERN itself, and just as a sort of brief word on what CERN actually is and what it stands for. And then the Large Hadron Collider, which is what gives us all of these interesting interactions that we are then studying with our detector, the Atlas experiment. And then at the end, I have a few esteemed colleagues who have kindly agreed to join a sort of panel at the end and be ready for your interrogation, anything that you should want to ask them about what it is they work on, or what life here is like, or how they are where they are, anything like that. I'm sure they'll be more than happy to answer. Okay, so I'm going to start with a little quote that I quite like. So this is from quite a famous philosopher of science who had this idea about how scientific knowledge advances. And he always thought about it in terms of paradigms. And so he said that any theory that's accepted as a paradigm in the scientific world must seem better than its competitors, but it need not, and actually never does, explain everything that it can be sort of hit with. And so that brings us on to what our theory is in the world of particle physics. So the sort of most successful theory that we have to date is what we call the standard model of particle physics, and probably a lot of you are familiar with this already. But this is a sort of graphic that just gives us the pieces involved in this endeavor. And so what we are usually talking about when we talk about particle physics is talking about these fundamental particles that make up everything in the universe and give us all of the physics that we see and give rise to all of the phenomena that we observe. And so it's a study of these fundamental particles and then the forces which kind of govern how they interact. And so we can kind of nicely divide this up into to a few different categories. So in the top left, we have the quarks. So on the leftmost column, we have these up and down quarks. And those are the ones which are kind of responsible for just about everything that we're familiar with. And so, you know, all of matter that we're familiar with, whether it's the steps that I'm standing on at the moment, or the laptop, or whatever it might be, are made up of compounds, of elements, which are made of atoms, and the atoms have these nuclei, and the nuclei themselves are made of these protons and neutrons. And we at one point thought that they were fundamental in themselves and that they couldn't be broken into anything smaller. And we now know that actually they are made up of these things called quarks, so these up and down quarks. But actually we have kind of different copies of these quarks, and so we have these sort of three versions of these quarks. So we can move up one column to the right, and we have these charm and strange quarks, and then up once again, and we have top and bottom. And we know that we have these kind of three columns, these three different versions of these quarks. We don't really know exactly why there are three, and the only real differences between them that kind of guide some of the other properties that they have are that they get heavier each time. So that's the quarks. They make up more or less everything that we know, along with one of the leptons. So that's the electron. If you see down at the bottom left-hand side, now we have these leptons. And again, there are these kind of three generations. And each of these leptons, these charged particles that we call leptons, that are also fundamental, that it can't be broken down any further, they also come with a corresponding particle that we call a neutrino. And they're kind of mysterious particles, and they can present some challenges even as we try and detect them. Sometimes people refer to them as being ghost particles. They're very difficult to detect. But with each generation of, so if you have the electron as the first lepton there, and it has a corresponding neutrino, the electron neutrino, and then we have the muon with the muon neutrino, and the tau with the tau neutrino. And again, they just get heavier each time. Okay, so that's the leptons. On the right-hand side, we have what we call the bosons, and these are the particles which carry the forces. And so we generally talk about the fundamental forces of the universe, and we talk about the strong force, the electromagnetic force, the weak force, and then gravity. Actually, the standard model of particle physics doesn't really have anything to say about gravity, and that's kind of a problem in itself on quite a grand scale. And so, in terms of the quote that I introduced, or that I started with, yeah, that's one of the things that this particular theory doesn't really have anything to say about. And then right in the middle of it all, we have the Higgs boson, which was discovered here at CERN only in 2012. So the ATLAS experiment and the CMS experiment discovered this boson, which had been predicted in 1964 by Peter Higgs. And it really serves as evidence for the sort of last piece in this theory, and that is the mechanism by which all these particles acquire their mass in the first place. And so, for me, that's part of the kind of excitement about now being here and working on ATLAS and on CERN, or at CERN, I should say, is that I was still at school when the Higgs boson was discovered, and I remember it being in the news, and I remember being very excited about it. But I never sort of imagined that I would get to be so intimately involved with some of these endeavors as I find myself now. Okay, that's our theory. I mentioned a few of the problems, and these are the kind of things that now we might want to try and devise ways of trying to sort of think about and figure out what the solutions to some of these problems are. So for a start, so this is this image here is actually from Hubble. It's this image of deep space, and you can see the kind of cacophony of activity that's happening in outer space. And one of the unfortunate kind of predictions that the standard model of particle physics makes is that this, along with everything else that we know, shouldn't really exist, because the standard model of particle physics predicts that matter and antimatter should be produced in equal amounts. And so when I was introducing the standard model just on the previous slide, we actually realized that all of these particles in the standard model have an antimatter particle associated to them as well, which is, again, sort of a copy of that particle, but with the charge inverted. And when antimatter and matter meet each other, in terms of when a particle meets its antiparticle, they basically just annihilate and give us out some energy. And so if they were produced in equal amounts, then it should have all annihilated by now. So this kind of asymmetry between matter and antimatter that exists in the universe and allows us to exist is another sort of open question. The other kind of embarrassing part of this, I guess, is that we don't actually understand an awful lot of the universe, in that about 95% of the universe is made up of stuff that we really don't know what it is. And so you have that little slither here in the composition of the universe that's this ordinary matter that we're kind of familiar with and that we've studied up until now. And then you have the other 95%. You have dark matter and dark energy, which don't interact in ways that we're familiar with at the moment. And we can kind of tell that they're layered by looking at the universe and making observations of galaxies and seeing the gravitational effects of dark matter, or witnessing how the universe's expansion would lead us to a belief in dark energy. But we don't really understand these things. So these are all kind of open questions. Okay, so then where does CERN come into the Standard Model and all of these open questions that exist in the world of particle physics? So if you were to be here in person and you were to take the tram out from Geneva out to the kind of outskirts to visit CERN, this is probably the first thing you'd see. So this is right out front of the main entrance to CERN. You can see the globe of science and innovation on the left-hand side there, and you see all the flags of the member states of CERN. And so CERN is a massive organization that was first established in the early 50s. And it was established really on the back of the Second World War with this idea that there should be a hub in Europe for science, basically. You know, there'd been a lot of Europe's scientific talent had been taken away by the end of the war, and there was this idea that really there should be somewhere that should be concentrated, and this is the sort of environment that CERN arose out of. And CERN had a few founding sort of principles, which were that, you know, one, that it should be this hub for European science, and it's gone on, you know, to be not just that, but a hub, you know, globally, but also that that the science that's done at CERN should not be linked in any way to military application. And so again, you know, this arose from the context of the end of the war, and also that the science done at CERN should be made public and completely transparent. So that was the kind of founding principles of CERN, and we arrive in a situation now where CERN really is a global leader, and not just that, but is this place where science happens on a kind of unprecedented scale. So I think there are roughly, you know, 15,000 people that make use of CERN and its facilities are in some way associated with it through the various levels of kind of membership and association. So it's really a huge amount of people worldwide. Okay, we mentioned the Higgs Boson as something that came out of CERN. Of course, there's a sort of natural fallout of doing these kind of experiments and doing science on this scale is that you have things and ideas that fall out along the way. So I always like this. This is one of my favorite examples, not just because it's a good example of something that came out of CERN, but because this plaque is right outside of my door, my office door at CERN. And so this is to commemorate where the World Wide Web was actually kind of first envisaged by Tim Berners-Lee at CERN. So it's just another example of one of the kind of fallouts that comes from doing science on this scale. But I mean, you know, there are countless. A lot of the technology that goes into our accelerators, our detectors, finds applications not just like the World Wide Web, where you have an IT application, but it might be in medical applications with cancer therapies, or there's a wide range of kind of fallouts. So for sure, if you'd come to visit in person, I would have taken you by this plaque and pointed it out. Okay, so what does it kind of look like at CERN? Well, I mentioned one of the other kind of big moments at CERN, which was the discovery of the Higgs boson. So this was in 2012 when that announcement was made. This is the main auditorium at CERN, and you can see the audience kind of gazing expectantly up at the screens here. And a few moments later, you know, as the next slide was hit, this is the scene. And so, like I say, I wasn't there. I was still at school at this point, but it made worldwide news, and you can kind of see the elation in the room. You know, some people that were there compared it to being at a rock concert. I don't know how many of them had been to a rock concert before, but the point stands that it was a very exciting time. What was it that they were all cheering? Well, what they were all cheering and excited about was this. So this was the kind of plot that was shown that that served as the evidence for the discovery of this this new particle, this Higgs boson. And so this was kind of the culmination of CERN down to the Large Hadron Collider down to Atlas. And so maybe I'll explain a little bit more about how that all happens and how you reach this point as we go on. But the basic point to realize here is that you have some idea for what you would expect to see if there were no Higgs boson. And then you go and you measure what you see in your detector, having set up a sort of stringent set of criteria. And what we find is that you have this kind of excess of events when you count them all up, where you have a reconstructed particle at a certain mass, and that is consistent with the Higgs boson. And so this is what they were all so excited about. Okay. So how do we do this? Well, the Large Hadron Collider. So the Large Hadron Collider is kind of the facility that allows all of this physics to be done. This is another one of my favorite quotes. This came from the House of Lords in the UK when the UK was carefully considering their sort of funding obligations to CERN. And so Lord Elton had said, "My lords, can my noble friend tell us what a Large Hadron Collider is and whether a smaller one might not do?" Okay, so what is a Large Hadron Collider and why might a smaller one not do? Okay, this is kind of an aerial shot of just outside of Geneva, and you can see the LHC ring traced along through the countryside. And so it sits roughly 100 meters underground, this massive tunnel that's 27 kilometers long. And you can see marked on this map various places. So we have the CERN site in the kind of towards the right-hand side there, the main CERN site. And Atlas is very close to that site. And we have these sort of 4 main points with big experiments at them at various points along the ring. And so you have Atlas there, along to Alice and CMS and LHCb. And these are all these detectors at the point that we collide protons. And so what are they actually detecting? Well, what we do is we send beams of protons around in opposite directions around this ring. And at these 4 points, these protons are brought into collision with each other. So they're actually in bunches, and that is the technical term. They're in these kind of bunches that are spaced, and in every bunch you might have 100 billion protons, and they're crossed over such that you hope that a few of them collide, and you can see what that looks like in your detector. And you hope that enough of them collide, and you cross, like I say, maybe 100 billion of these protons, and you might expect to see around 20 collisions or something like that. And we cross these bunches every 25 nanoseconds. So that's 40 million crossings per second. And I'll talk a little bit about the detectors and then what goes on at those points where you cross and collide the protons. But this is what the Large Hadron Collider is doing. Why does it need to be so big? Well, the trouble is that as we accelerate these protons, it's a bit like swinging faster and faster on a roundabout. The faster you go, the stronger you have to hold on to the roundabout in order to not fall off. And how we hold these protons going around in this big ring is with magnets. And so we currently have the magnets about as powerful as we can get them in order to be able to still hold them in this ring. Were you to have a smaller ring, you would need even more powerful magnets to be able to send them around at anything like the speed that they are sent around at, which is virtually the speed of light. So this is sort of the answer to why a smaller one might not do. You would run into sort of all sorts of problems. Famously, the magnets in the Large Hadron Collider actually have to be held at extremely low temperatures with liquid helium, such that the Large Hadron Collider is one of the coldest places that you'll find anywhere in the universe. It's even colder than outer space. And so I think that the magnets get cooled down to 1.9 Kelvin. Maybe someone correct me if that's not quite right. But whereas at outer space, I think you're at about 2.7 Kelvin. So it's incredibly cold. These magnets need to be. Okay. CERN is a massive complex. It's not just the Large Hadron Collider. So this is the whole kind of complex. I won't go into all of this, but the point is that CERN is kind of built up over the decades. The Large Hadron Collider is kind of the latest and greatest tool in the arsenal of the particle physicist or the experimentalist, but it's kind of standing on the shoulders of the proverbial giant in terms of the other accelerators that now feed into the Large Hadron Collider. Okay, so that kind of brings us down to the ATLAS experiment, which is what's over my shoulder. And so ATLAS itself is another sort of massive collaboration that exists within CERN. So there are thousands of scientists working on ATLAS alone, and you can see the institutions worldwide that are involved in the collaboration just on the map here. And so points to anyone who can guess what ATLAS stands for. It's one of these kind of, it's a bit of a stretch of an acronym. So ATLAS stands for a toroidal LHC apparatus. So I'd be very impressed if you would have guessed that from the name. And so ATLAS is one of the four main detectors at CERN. And along with CMS, it's what we call a general purpose detector. So this is a kind of an image just for scale, and you'll get some kind of live images in just a second. But hopefully from this you can get an appreciation for the scale of these things. So this is during the construction of ATLAS, and you can see down at the bottom there's a man standing there. It gives you an idea for the size of things. So there's this kind of inherent juxtaposition between wanting to measure these almost infinitesimally small particles and facets of nature, but requiring a 27-kilometer collider along with these massive bits of machinery to do so. This is actually from just where I'm standing now, or just to the left of me. So this is the view that you'll get in just a second. But you can see, this is just one end of the ATLAS detector. And actually it's about 25 meters tall and about 40 meters long. So, even in trying to get as much of it in as you can, you're only ever going to be able to see a small part at any one given time. It sits in this massive cavern 100 meters underground, and even in the cavern you're kind of almost pressed up against the wall just by the size of the thing. Okay, so that's all very good. That's the first sort of defining characteristic, is the size of the thing. But what does it actually do? So ATLAS is like I say, what we call a general purpose detector, meaning that it's designed to sort of collect information on as broad a sort of number of characteristics of these particles that you might see in a collision as is possible. So you collide some protons, and what you get out are maybe some particles that you're interested in and you want to study. But actually, quite often what's going to happen is that these particles are going to decay, and we don't see what's created in the first instance. What we get is a sort of mess of other things. So it becomes a sort of puzzle of trying to work backwards to piece everything together to work out what was there in the first place. So it's a bit like, coming into your house and finding a load of smashed glass on the floor and then trying to piece it all back together and work out what was there in the first place. And so Atlas as a detector is made up of many sort of sub-detectors, each of which are designed to determine different characteristics of the particles which interact with those sub-detectors. And so I'll talk about that in more detail when I go to actually to show you this live. But that's the broad principle. And so these each of these sub-detectors, these layers of the detector, are designed to sort of provide you information on different kinds of particles. And so you can see here the kind of concentric layout of the detector and the different particles which each layer is designed to be able to provide you information with in order that you can reconstruct the sort of event, the actual sort of physics that happened in the collision that you're interested in. So in some sense, Atlas can then act as something of a giant digital camera, and this is actually a sort of reconstruction of what we see in an event. So I always choose this one because this is a reconstruction of the kind of event that I tend to look at. And so this is where we have two. So we have a top quark and an anti-top quark. So these are the heaviest of the quarks, and we have them decaying in various ways. And you can see that they're reacting with all the different parts of the detector. And we have these big cones, which are kind of these sprays of other particles that we need to piece together and be able to group together to actually decide what we had in the first place. Okay, so hopefully that has given you some idea of what it is that we're trying to do here and what this detector is actually designed to do. So now what I'll do is, if you just give me a second, I'm going to turn the camera on over there, and then we'll have a look at the detector itself. Okay. Okay, almost there. So maybe at this point, if you could spotlight the other video, and then we should be good to go. Sorry? Ah. Yeah, perfect. Okay. 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 So here we go. So hopefully now you can have a kind of a live view of the detector itself. And so we're at one end here. So actually the cavern extends all the way down there. Like I say, it's about 40 meters long, and so the detector itself is about half the size of Notre Dame Cathedral, and it weighs about 7,000 tons. So it weighs about as much as the Eiffel Tower. What you're actually looking at, the sort of grand structure on the end here, is part of one of the subdetectors. So there are three main sort of systems involved in the detector. There's the most central part that we call the inner detector, which is the tracking system. There's another system which is just outside of that called the calorimetry system, which is concerned with measuring the energies of these particles. And then there's this whole dedicated system on the very outside, which is designed just to look at these particles called muons, which is this kind of heavier copy of the electron. And so it has its own dedicated, these muons have their own dedicated system that sits on the outside. And the reason for that is that the muons are actually very penetrating particles, and so they're almost the only particles that pass through the rest of the detector. And so by the time they reach this outer system, which is the muon spectrometer, the only particles that should reach that part are these muons. And so what then are we actually doing? Well, the whole detector is encapsulated in a massive magnet system. And so we have these toroid magnets. And so we can see, I'll try and bring the camera this way and you might be able to see. You can see these kind of barrels that are sitting with these kind of orange stripes around them. And so this is one part of the toroid magnet system that covers the sort of barrel section of the detector. We also have on each end these sort of toroid Endcap magnets. So this is one of them just here, this silver structure directly opposite with me. And usually this would sit just inside, but it's been moved out of the way to allow for the people working on the detector to be able to get to other parts. But usually this would sit back on the end. And in this way, this magnet system encapsulates the whole detector, so that when these muons, which are charged particles, are created, they're actually going to be, their paths are going to be deflected by this magnet system. And by looking at how they interact with this muon spectrometer, and so we can reconstruct the sort of paths that they take, and we can make measurements of the momentum of these muons by doing that. So that's the muon spectrometer. This is the big muon wheel. The calorimeters sit just inside, so they're the kind of middle system. And so I'll do a swap with Savannah, who's helping with the camera. And so you can actually see right in the middle here, this kind of central part of the detector. This is one of these, what we call the Endcap calorimeters. And so again, the calorimetry system is designed to kind of encapsulate as much as is possible of the center of the detector. And so if you imagine where the beam is going to come, it's going to come right along and through the central part of the detector. And actually, if you look closely, just right down in the middle of that Endcap calorimeter, you can see where the beam is going to pass through. And so as the collisions happen right in the heart of the detector over to the right-hand side here, and you have particles come out, there are two parts to the calorimetry system. So the first part is the electromagnetic calorimeter, and it's designed to measure the energies of particles such as electrons and photons. And so they will be kind of absorbed by that system and have their energies measured. And outside of that, we have what we call the hadronic calorimeter, and that's concerned more with basically what's going to arise out of the decays of quarks. And so if you remember, I mentioned these kind of sprays of particles that we sometimes get. that's where they're really going to show up. And so these tend to be these kind of bound states of the quarks that we call hadrons. So I mean, they could be protons. They're unlikely to be. What we see most of the time are these other particles called mesons, where we have two quarks that are bound together, and they will again be absorbed in this hadronic calorimeter, and we'll be able to measure their energies. And so you can start to kind of develop a picture of how this puzzle is built up. If you start to piece together muons from the muon spectrometer, electrons and photons in the electromagnetic calorimeter, and then these hadrons in the hadronic calorimeter. At the very heart of the detector and closest to the beam itself, in fact, at its closest approach, the innermost layer is only about 3 centimeters from the beam itself, and that is the inner detector. It's what we call the tracking system. And what it is basically layers of these silicon detectors. And again, it's kind of a piecing together question. So we look at where particles have interacted with this with these layers, and we can kind of build a track, a path that the particle has taken by more or less joining the dots of how they've interacted in these concentric layers of the tracking system. The key to that is another magnet system. So the whole tracking system actually sits inside the solenoid magnet. And that solenoid generates a magnetic field, which again would deflect charged particles. And so once you have the path that has been followed by one of these particles in the tracking system, you can infer its momentum from that. And so you can see that really what the detector is doing in its various systems is giving you pieces of information to bring together to decide what exactly was happening in the first instance, right at the heart of the detector when the collision took place. And by sort of choosing how you want to, what criteria you want to apply to the particles you're interested in, and then looking at what it is that you see in the detector and comparing that to what it is that you were expecting, then we can make certain sort of conclusions about the physics that we're trying to interrogate. And so that's kind of an overview of the detector. I never get bored of coming down here. The corner, let me see if I can do a live walk for you. So this is my favorite part every time. We're going off script here, but this is my favorite part. In a normal visit, we come through this door, and we come around this corner. If you see Savannah there, that's usually my part. So I'm usually leading the way so that I can look back in the same way Savannah's doing and watch people come around this corner and see Atlas for the first time. And that never gets old to me. Okay, so I think that's probably us as far as a sort of an overview, a live overview of the detector is concerned. So what I'll do now is head back. So I'm just going to stop the video here and return to my old post. Okay, so what we'll do now is that we have a variety of esteemed scientists standing by, some of the very best that Atlas has to offer, waiting to answer your questions. And so what I'll do is, so we have Savannah, who's been here helping me with the camera and things. So she's a PhD student at Manchester. I should have introduced myself a bit better. I'm doing a PhD at the University of Glasgow. And then we also have Marin standing by, who's also doing a PhD at Atlas. And we have Federica, who has a research position at the University of Glasgow, but works in Atlas as well, and in many ways is my boss. So I have to be on my best behavior. So I'll let them now maybe just in turn kind of give a brief introduction as to who they are and what they work on, and then we'll all be happy to answer your questions. So maybe Savannah, if you want to start.
Yeah, so hopefully you can hear me okay. It might be a little bit noisy because I don't have a microphone as good as Adam's got on at the moment. But yeah, hi, I'm Savannah. As Adam said, I'm a PhD student at the University of Manchester in the UK. And specifically, so I work for the Atlas detector as well, but I do precision tests of our standard model of physics. So Adam spoke a bit about the standard model, but how we know that it must be wrong somewhere or it must fail somewhere. So I work to test it really hard to see where it breaks. Unfortunately, we haven't found where it breaks yet, but we keep looking and hopefully one day we'll find something. So, yeah.
Okay, thanks. Marin, do you want to say a few words?
Yeah, hello everyone, I'm Marin. I work on the Atlas experiment, and in particular what I do is study a rare process with top quarks similar to Adam, and like Savannah was saying, studying this rare process is trying to uncover where the standard
You muted yourself.
back now. And another thing I do is I prepare data from the Atlas experiment for use in education related to what you'll be doing tomorrow.
Okay, thanks, Mary. Federica, do you want to say a few words?
Hi, I'm Federica, and yeah, as Adam said, I work in Glasgow. I'm a researcher there, and I also work on the standard model physics because, as Savannah said, I think it's the most interesting thing, because if you don't understand, if you're not trusting the model that you use to search new physics, you cannot really find anything new. So I think it's a very important job, the one that we do. I also work on the top quark, and what you can see in the back is an event that has been recorded from Atlas, where there are two tops. And yeah, so we study these kind of events and try to understand if the way that we have to describe them is appropriate or if there is something new. And this particle is super interesting because it's the most heavy one that we have at the moment in the standard model. So it should be very connected with some new particle that we may observe.
Okay, thanks, Federica. So yeah, at this point, I guess we will more than happily do our best to answer any and all questions which any of you might have for us.
Okay, so we have a first question in the chat asking, how many hours of continuous functioning Atlas has?
Oh, so that predates me. So Atlas has been online in sort of different periods of data taking since the LHC was first turned on around 2010. In terms of continuous hours of, I think I would need to do a calculation. I don't know if there's maybe someone has a figure for some of this.
I mean, about hours, yeah. Yeah, maybe we can say a little more about how Atlas works usually. So when there is a good year, like 2018, for example, it's been a very good year. Atlas works basically like all year, apart from some technical stop that we had to have, like few weeks where we need to stop for like adjusting the detector. And then there is usually a longer stop over Christmas that it is needed for larger intervention in the detector. And then every few years, we have a longer stop where there are large changes in the detector, or we change our, like, if LHC change, for example, we had one of these long stops. The last one was in 2014, because then we restarted in 2015. And during this period, we moved from 8 to 13 TeV. And it's more or less the same thing we are doing now, where Atlas is not running because we are changing the energy of the beam.
Okay, thank you very much for that. We have two questions. One from the chat. We saw a movie that said that there is a risk that you can create black holes small inside CERN. Is that true? Is it possible that you can create small, very small black holes?
So my understanding of this is that you can get these kind of microscopic black hole-like objects, maybe a possibility, but that they evaporate actually almost instantaneously. And so actually one of the interesting things about the LHC and the LHC operates at the highest energy that any collider ever has, and we're colliding these particles at a higher energy than we ever have before, and at the very edge of our abilities. But actually, in nature, you have collisions happening at higher energies sort of constantly. And so we have these really high energy particles coming from outer space called cosmic rays. And they will collide with other particles in the Earth's atmosphere at energies much higher than those that exist at the Large Hadron Collider. So usually this question is asked in the context of CERN's world-destroying capabilities, and I think that's how I would get myself to sleep tonight, thinking about that. Is that actually we've done very well to get to energies as high as this, but actually in nature there are collisions happening at even higher energies than that. But I don't know if anyone else knows maybe more about these events than I do.
There is a follow-up from that, and how do you know that they evaporate, the black holes? And this is a question that you get from the students.
So to try and answer the question, how do you know they evaporate? We would, Jenny's posted the video, we would aim to observe what they transform into when they evaporate. So it might be photons, for example, the particles of light. And also they aren't like absorbing anything as you think of astrophysical black holes doing. So if they're not absorbing anything, then they're not an issue. They're not dangerous. I think that would be what I'd say to students.
I mean, if I can add something on this, I love this story of the black holes, because this is a bit more complex, but I think it's very interesting, and also like show you how are the things that we don't know. Basically, on the edge of the black hole, it is black because light cannot go out, right? So if a couple of particles is created there, then one of the two particles can run away, but the other particle is like sucked inside the black hole. And so since the energy is conserved, that means that the black hole gains some energy from this particle, and this is the evaporation basic concept. But we should be able to observe the particle that escape. This is called the Hawking radiation. So this is also what we are searching for, the black holes evaporation.
There are a few questions actually from Facebook. The first one is about sources of noise. So what are the main sources of noise that you have to deal with?
I would say the main sources of noise, I'm not exactly sure if it's what you mean, but the main sources of noise in any study that we're doing is what we call background processes that were discovered a long time ago and have been really well studied, so we don't need to study them in as great a detail anymore. But other noise processes can be from things like cosmic rays coming from outer space, but they are very well understood and accounted for. It helps that the Atlas detector is 100 meters underground. That's very good for stopping cosmic rays.
Thank you.
Yeah, I think the other thing to add to that maybe is that, as Marin was saying, you know, in any kind of given event that you're looking at, there could be all sorts of noise coming from the fact that, like I say, when you cross these bunches of protons, you don't just get one collision, and even of that collision, maybe you're only interested in one small part of it, and so it's kind of a whole complicated endeavor to try to separate out the parts of the collisions that you're interested in from this other stuff, which you could sort of think about as noise or contaminating the sort of interesting physics, so to say, that you're trying to look at. So in terms of on an analysis level, I think maybe those are kind of sources of noise. On an actual hardware level, it's kind of a different thing as well, because like Federica was saying, there are various stops where the detector isn't running and maintenance is done or upgrades, and part of that is that actually all of this radiation that's constantly being created at the heart of the detector, it sort of degrades the detector performance over time, and so maybe parts need replaced, or as like we're aiming to do in sort of a few years' time, we want to have basically more collisions happening, which means that these pieces need to be more resistant to the radiation, and you get all sorts of electrical noise in the parts of the detector that come from this degradation, and so you need to be able to know that you're capable at the level of all of those different subsystems of separating out what is a real interaction that's happened with some particle traversing your detector, and what could just be kind of spurious noise that's coming from the fact that some of these materials have been degraded over time.
Okay, thank you very much. So we have a couple of questions, some from Facebook and one from here, and I will group them together because they are common themed, let's say. So we have, has the standard model yet broken down? This is number one. Number two, how do you detect an unknown product of the collision? Number three, if you had a wish, what would you wish to be found by Atlas?
My answer on my wish. So since we work on top physics, basically me, Adam, and Marin, we of course want to find a new resonance decaying to two tops. So that would be great to observe, actually. That would be a very heavy particle. But this is just, I think, for us working on top physics. What everyone in Atlas hope to find, I think, is SUSY. And this is a fancy name to a new theory that basically says that every particle that we have already have observed should have a partner that is very, 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 very heavy, so difficult to find. And there are a lot of searches on these. And if this new theory is true, that they have a lot of nice impact on other things. Like, for example, it would be possible to, this is hard to explain, to bring in a bigger picture all the interaction that we have at the moment. And so that would be very nice from theory point of view, even if hard to explain. But it means also a lot of new particles. And now I forgot the first two questions, sorry.
Okay, so thank you. And we have a student question.
No, wait, sorry, Annalise. So the questions were if the standard model has broken down yet. I think no, but okay. And how do you detect a new product of a, yeah.
Sorry, the standard model, yes and no. I mean, we didn't find anything sure, but there are small deviations here and there, indicating that maybe the standard model is not complete. And for sure, there are things that we don't know. Like, for example, the dark matter is a big, oops, the standard model is definitely broken because we need to find something to explain it, and we haven't found it yet. How we find a new particle? So we basically search for something that we know, like, for example, two particles that we know very well, for example, the electrons. And then we search for the mass of these two electrons. And this mass should be very flat if there is nothing. If these two electrons come from random collision, you don't expect them, like, the mass to, so the probability of the two electrons having a certain mass is very flat because you don't expect them to have a certain mass. There is no reason, unless they were combined in a particle and then the particle decay, and then that particle, I mean, you should be able to observe a peak in the probability on that particle mass because there is something there. So if you really look at the mass of these two quantities that you know, like the two electrons, and you look at the full spectrum of these, if you see a peak and you weren't expecting a peak there, then you find a new particle. So this is the main approach to find new physics, as in terms of new particles.
So I think at this point, Savannah and I are going to have to drop off just before we start getting shouted at for being down in the cavern too late. So at least for us, I think we need to say goodbye at this point. But yeah, I want to say thank you again to everyone for taking an interest in what we've obviously found interesting enough to kind of embark on this endeavor. Hopefully, you have some idea for how the detector works and the kind of things that we're looking for and how we go about finding them with the detector. Yeah, I don't, you know, if Marin and Federica want to answer more questions, then feel free. Savannah and I at least will need to drop off for just now. So sorry that we couldn't hang around to answer all of the questions, but yeah, we're going to need to head back to the surface.
Thank you very much. Thank you very much for the great tour.
Okay, thank you.
This was really great. Thank you so much for your time.
Thank you very much. One more question, and then we will be done. What do you think? Okay. I think there is one question which asked about black holes, right?
Yes.
It was a student question. So a student asked if we could be able to create a small black hole that does not evaporate at an instant, meaning that we could observe them more and get knowledge about what exactly is inside them and how could we use them.
Well, I would say that would be amazing. That would be another really nice way of studying black holes, other than the astrophysical ways to study black holes. It'd be great, but we're not there yet. Not sure if it's possible.
Also, evaporation rate doesn't scale inversely proportional with the black hole area. This means that the smaller the black hole, the larger the rate. There is a relationship there. So it means that tiny black holes actually evaporate instantly and produce symmetrically in 4 pi Hawking radiation. So many jets and particles and so on. So, okay. Do we have any other question? Okay, I see that we don't. So I think that this is a good moment to say that we close for the day. And okay. So, okay.
No, I just wanted to thank again everybody at CERN and Federica and everybody. Thank you so much. This was really great.
Thank you.
It was really a pleasure to have you with us.
Thanks a lot, and for all the participants, see you tomorrow.
So yes, for everybody else, we reconvene tomorrow at 10 a.m. Central European time. Same link, same place, and see you tomorrow. Bye, everyone. Nice evening. Bye, everyone.
Thank you again. Thank you very much.
Bye, everyone.
Thank you for being here.
Thank you
so much.
Very much.
Bye.
Bye.
Bye, everyone.
Thank you very much. Bye.